Okay, just a couple of quick calculations with heat engines. First off, if we know that a heat engine does 8,500 joules of work, but it exhausts 14 kilocalories of heat, then we can find the efficiency of that engine. So if you remember, efficiency was the work out over QH. So that's what we're trying to find. We need to figure out where these numbers go. We essentially have four things we're dealing with in all of these problems. We've got efficiency, QH, QL, and W. And in this case, we're trying to find efficiency. We're given 8,500 joules of work, so that goes here. And exhausting heat, that goes here, QL. That's the low temperature, the heat that flows out to the low temperature side of the engine. And that's 14 kilocalories. Now, we need our units to match for our efficiency equations. So we can go ahead and multiply this guy by 4,186 joules per kilocalorie. And that's going to give us a big fat 58,604 joules of waste heat. So we don't have QH here, but the other equation that we know that's always true for heat engines is QH equals W plus QL. So if we plug in this for QH, we've got work over work plus waste heat. And now we can plug directly into this guy. If you prefer, you could plug in W and QL here and get QH and then plug QH in. It's all the same. So we're going to have 8,500 joules on top and 8,500 plus 58,604 downstairs. Quick little calculation, multiplying by 100 to change it into a percentage, and this rounds to 12.7% efficiency. Alright, one more. Heat engine has an ideal efficiency. So ideal efficiency is a different equation. This is also known as Carnot efficiency. I'll kind of go back and forth between the terminology. I think your book usually uses ideal efficiency in the homework problems. Anyway, ideal efficiency is 38%. Cold reservoir, that's another term they use for the cold side of the heat engine, is the cold reservoir, is 180 degrees, and the hot side, we like to call that the hot reservoir. So with ideal efficiency, we have the efficiency, and we've got TL, and we've got TH. We're not worried about the work at all. These are the only factors we have in our equation. If you remember, ideal, I'll just put ID, was 1 minus TL over TH. Now, one thing I didn't mention earlier is when you're plugging in these temperatures, they have to be in kelvins. Okay. Now you might think because it's a ratio that will cancel out, but not with temperatures, because you're not multiplying them by a factor, you're adding it. So adding 273 to top and bottom is not going to cancel out. That's not how algebra works, right? If you have x1 plus 273 over x2 plus 273, that does not equal x1 over x2, right? So you have to do it in kelvins. Another way that we know that, let me erase this and get it out of the way, is if we look at what has to happen in order for our ideal efficiency to go to 100%. Basically, either we want to subtract nothing from 1. So this has to either go to infinity, which isn't going to happen, or this has to go to 0. And having a high temperature of 0 degrees Celsius, then your low temperature would need to be lower. But you could do that. You could have that as negative 20 degrees Celsius or whatever. That's going to give you 100% efficiency? No, that's not. You have to have absolute 0, and then you could get 100% efficiency. But you're not going to get to absolute 0 anyway. So anyway, just make sure that you have these temperatures in kelvins is the moral of the story. All right, 1 minus our low temperature. Actually, I'm going to write this a little differently so it's just easier to do the algebra. So the efficiency we're given is 38%. Be sure and make that a decimal. We have the low temperature is 180. We're going to add 273 to that guy. And we're trying to find the high temperature. Okay, so if I'm going to start plugging into this guy, I've got 0.38 equals 1 minus the low temperature, and 180 plus 273 is going to give you 453. And then we're going to solve for that high temperature. So now we just have a bit of algebra to take care of this. If I switch the sides around a little bit, I'm going to get 453 over TH equals 1 minus 0.38. So I added this to that side, subtract that over there. And then I'll rearrange things a bit again, and if I multiply the TH up over there, divide this stuff down over there, then I'm going to get 453, and 1 minus 0.38 is 0.62. So there we go. Throw that in your calculator, and we will get 730.6. This answer is going to come out in kelvins. I think most of the answers that I'll give you are in Celsius. So subtract 273 from that guy, and you get 457.6 degrees Celsius. All there is to it. Nice and easy. See you next time.